Okay, good morning, guys. Happy Monday. So this lesson is scheduled for Tuesday, but I'm just putting it up a day in advance. So today's lesson is on 7.2. Hopefully you did 7.1 and did all the homework questions and understand the concept behind equilibrium, and you've completed the Google form as well. So just so you know, I will be giving you a mark out of 5 for the Google form, so please complete that before tomorrow because midterm marks are due by Friday of this week. So I believe that will be your last mark, other than if I get the 7.2 assignment marked. I'll include that as well. Okay, so today we're going to be learning about 7.2. Our learning goals are analyze equilibrium expressions and equilibrium constants for a variety of reactions, study the magnitude of the equilibrium constant and predict whether a reaction or, this is a typo here, or product is favored, the reactant is favored, or neither. So again, you'll know what this means after the lesson. So once a system reaches equilibrium and all conditions remain constant, a ratio of the concentration of products to reactant can be determined. This formula is used to calculate where along the equilibrium the reaction is, and it is called the equilibrium expression. The calculated number value is called the equilibrium constant, or KEQ, which you're going to become very familiar with. Okay, so you can get it from the balanced chemical equation. Okay, so we are allowed to use the coefficients in the balanced chemical equation, which is very different than what you learned in chapter 6 when you were doing the rate law and you could not use the balanced chemical equation. But in equilibrium expressions, you can. So the general equation is KEQ equals the concentration of your products raised to the exponent of the coefficient in front. So concentration of C here raised to the exponent little c times the concentration of D raised to the exponent little d divided by the concentration of the reactants raised to the exponents of the balanced chemical equation. Okay, so remember all these concentrations here represent the concentrations at equilibrium, not the initial concentrations, not the change, but at equilibrium. So we're just going to go over some definitions here, homogeneous versus heterogeneous. So homogeneous means all reactants and products are in the same state. Heterogeneous means reactants and products are present in at least 2 different states. So like, let's say one is a gas, one is aqueous. So here's some key points. Solids are never included in the equilibrium expression. They have constant concentration density, so they do not affect the equilibrium concentration. Pure liquids are also not included in the equilibrium expressions, as long as it is only liquid or aqueous that exists on both sides. If the liquid is diluted by so if it's aqueous, it is included. K gases and aqueous species are always included. So anything that's a gas or AQ is always included in the equilibrium expression. Solids and liquids are not. Okay, so let's do some examples. So write the equilibrium expression for the following. So you are going to have to watch the next video to get this example. But basically, I'm going to tell you the KEQ is the concentration of the products divided by the concentration of your reactant. So it's going to be HBr raised to the exponent of 2 divided by H2 raised to the exponent of 1 times Br2 raised to the exponent of 1. Okay. Oh, I did a mistake there. I included Br2. You are not supposed to include a liquid in your KEQ expression. Okay, so make sure you look at the states when you're doing your KEQ expressions. For this one right here, you want to look and see which ones are liquid or solid, and there's 2 liquids here, so these are not going to show up in our KEQ expression. Okay, so just watch the next video for the correct answer. Okay, so once we have the equilibrium expression and the relative values of concentration, the KEQ can be calculated. So if KEQ is equal to 1, that means you divided the products divided by the reactants, and they're approximately equal, right, because it equals 1. So the reaction is balanced. So that means neither the product or the reactant is favored, and I would say that where the reaction lies is at equilibrium. Okay, if KEQ is really small number, like way less than 1, that means the reactants are larger than the products at equilibrium, and therefore the chemical reaction is lying to the left, like towards the reactant side. If KEQ is greater than 1, the reactants are smaller than the products, and the product formation is favored. Okay, so that means the equilibrium has shifted way to the right. Okay, so if K is the equilibrium constant for the forward reaction, then 1 over K is the equilibrium constant for the reverse reaction. You just simply flip it. Okay, and this is example number 2. Calculate KEQ, or equilibrium constant, for the following reaction, given the equilibrium concentrations of all of these in the chemical equation. So just watch the next video for that example. Okay, so at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So the ratio of the rate constant for the forward reaction divided by the rate constant for the reverse reaction is equal to the equilibrium constant. So I encourage you to look at the textbook for this derivation. It's just very interesting because it actually proves this definition that the rate of the forward reaction is equal to the rate of the reverse reaction. Because when you divide K forward divided by K reverse, you get KEQ. Okay, so please complete the assigned homework for this, and you will be marked for 7.2 activity/lab, which I will be posting right beside this video in the post, and the rubric is posted there as well. So I just want to show you what I'm referring to. So if you look at investigations, okay, and you go to, I believe this is page 473, but this is attached as a PDF file under this attachment. So this is what you're doing. So the equilibrium law, so you're reading it, and you are testing out the equilibrium law with this data that's given to you in the chart. Okay, and you are going, so we're going to go to the next page, 474, and you're going to complete these questions here. Okay, and check the rubric for submission, and it's due on Thursday. Okay, another thing I want you to read through is make sure you read through the textbook because it explains how they came about with the equilibrium law. So they said, to see how the equilibrium law is useful, consider the formation of hydrogen iodide HI from its elements. So the balanced equation is H2 plus I2 makes 2HI. So it shows the results from an investigation to observe how changing the initial concentration of the reactants and products affected the equilibrium. The reaction was allowed to proceed to equilibrium in a sealed 2-liter flask at 485 degrees Celsius. Okay, so they got some data for this reaction, the initial concentration, and then at equilibrium, they got the concentration of all the reactants and products. And then the data from each trial was entered into the equilibrium law equation, which is K equals the concentration of the products divided by the concentration of the reactant. And what do you notice about the value of the equilibrium constant? So we did trial 1, trial 2, trial 3, and notice all the KEQ value is the same. So that means the equilibrium constant, the law, is correct, right? Because they did several trials, experiments, and it proved it correct. Okay, so I encourage you to read through the textbook as well, and they have lots of tutorials, but watch the next video to see the 2 examples that I'm going to take up. Okay, so that's it for today.